In this video, we'll look at handling of numbers of scientific measurements. So in the previous video, we talked about scientific measurements, so simply measurements. And to handle these scientific measurements, there are two important techniques of handling scientific measurements. And these are, so we have two important techniques of handling scientific measurements. So the first one is scientific notation, and the second one involves the use of significant figures. Significant figures. Okay, so let's start with the first one, which is scientific notation. So scientific notation actually is used when handling very small numbers or very large numbers. So for scientific notation, you should know that numbers are written in the form of n times 10 to the power n. N times 10 to the power n, where this n, capital letter N, is the number between 1 and 10. Then this small letter n can be a positive or negative integer. Okay, for example, let's say we measure the mass of a substance to be 0.0000025 grams. So what would be the best way to report this one? Of course, it's to use what we are calling scientific notation. So we have to make sure that this decimal point is moved to the right. It has to be between 2 and 5. So it will move how many steps? 1, 2, 3, 4, 5, 6. So it will be 2.5 times 10. So the decimal point moved how many steps? 6. 6 steps to the right. So whenever a decimal point moves to the right, the power should be negative. So it's negative 6 grams. We have written in standard form. Same way, let's say we have a very big number like 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, like that. Let's say kilograms. So that is a very big number. So the best way to report this one, of course, is by use of scientific notation or standard form. So we'll simply count the zeros. I mean the number of steps the decimal place will move. So it's there to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it will be 8 multiplied by 10 to the power 11. The power is positive because the decimal point is going to the left, kg. Yes, so this is the first important technique, the use of scientific notation, writing the number in that format. Okay, now what we should know is how to do calculations. How do we perform calculations when dealing with scientific notation? So calculations when dealing with scientific notation. Okay, and the first thing is what? Addition. Let's talk about addition and subtraction. So in dealing with scientific notation, how do we add and subtract numbers which are written in scientific notation? For example, let's start with let's say we have 7.4 times 10 to the power 3, then plus, let's say 2.1 times 10 to the power 3. Okay, so in handling these numbers in scientific notation, the first thing which we have to do, so as you can see, we are adding this one and this one, we are adding these. So the first thing you should do checking the powers on these tens. Yeah, check the powers. So for this one, it's power 3, power 3. So that's the first thing. You confirm if the powers are the same or they are not the same. So if the powers are the same, you should go direct to performing your calculations. Otherwise, if the powers are different, you have to make them the same. We'll look at that. But now we can make them the same. So at this point, just go direct. So what you actually do here is that if the powers are the same, it's possible to factor out this 10. So you simply add 7.4 plus 2.1, then factor out the 10. So you write it like this: 7.4 plus what? 2.1. Then multiply by 10 to the power 3. You have factored out the 10 to the power 3. As you can see, it's possible to multiply back 10 to the power 3. So this will be equal to 7.4 plus 2.1. That's about 9.5. Yeah, 9.5 times 10 to the power 3. Just like that, you have added. So that's how you go about them. Let's look at other examples. Okay, let's say we have the second one there, B. So for B, what if we have 4.31 times 10 to the power 4, then plus 3.9 times 10 to the power 3. Okay, so how can we deal with this? So the first thing, check if the powers on these 10s are the same. So there is power 4 there, power 3. The powers are not the same. So make sure that the powers are the same. So you can choose either to change this one to power 4 or to change this one to power 3. Both ways will work. Okay, so let's try both. We first change this one to power 4, then we'll do it again. We'll change this one to power 3. You'll see that we still get the same answer. So here we have 4.31 times 10 to the power 4 plus, so this is 10 to the power 3. We want it to be 10 to the power 4. So this decimal point, should it move to the right or to the left? So when it moves to the right, remember we are getting negatives, so it's just to move to the left so that we can have a plus 1 there. So it has to move to the left by a step so that we can have 0.39 times 10 to the power 4, right? Yes, so same powers. From there, just adding 4.31 plus what? 0.39. Then you factor out 10 to the power 4. So times 10 to the power 4. This will be equal to what? Okay, so let me just punch that on the calculator. So we have 4.31 plus 0.39. It's 4.7. So we have 4.7 times 10 to the power 4. You are done. Let's do it the other way around. Let's change 10 to the power 3 to 10 to the power 10 to the power 4 to 10 to the power 3. You'll see that you get the same answer. Okay, so how can we change 10 to the power 4 to 10 to the power 3? So this decimal point has to move where? To the right, so that we can say minus 1. Otherwise, if it moves to the left, we'll say plus 1. So we have 43.1 times 10 to the power 3, right? Then plus, we maintain what we have, 3.9 times 10 to the power 3. So here we add 43.1 plus 3.9. Then you factor out times 10 to the power 3. So this will be equal to, let me just punch that on calculator. So 43.1 plus 3.9. Okay, so we are getting 47 times 10 to the power 3. Then in this case the decimal point is there. So is 47 times 10 to the power 3 in standard form? No, this is not the standard form or scientific notation. So this decimal point has to move one step to the left to be 4.7 times 10 to the power 3. to the power 4. Since the decimal point has moved by a step to the left. So as you can see, we are simply getting the same answer. So the choice is yours on which one to change. Just make sure you report the final answer in standard form. Okay, let's look at another one. So for C, let's say we have 2.22 times 10 to the power negative 2. This one minus, let's say 4.10 times 10 to the power negative 3. Okay, we're handling this one. In this case, we are subtracting. So even for subtraction, ensure that the powers there, the powers of 10 are the same. So this is negative 2. That is what? Negative 3, right? So you can choose on which one to go with. Let's say we choose to go with negative 3. So we have to change this negative 2 to negative 3. Okay. So how can we change it to negative 3? We have to make sure that this decimal point moves to the right. Otherwise, if it moves to the left, we'll add plus 1. If it moves to the right, we'll say minus 1. So this one has to be 22.2 times 10 to the power negative 3 minus 4.10 times 10 to the power negative 3. Okay. So this will be equal to, just get 22.2 times 10 to, let me write that again. We have 22.2 minus 4.10, okay, then times, so 10 to the power 3, 10 to the power 3 is factored out. So this one will be equal to what? Let me just punch that calculator. So we have 22.2 minus 4.1. So we're getting 18.1. We have 18.1 times 10 to the power negative 3. Now can we leave it like this? No. We should just have one number before the decimal point. So meaning it should be 1.81 times 10. Then the decimal point has moved to the left. So what do we do? It's plus 1. So it's negative 3 plus 1 should be negative 2. Okay, so that's how you go about addition and subtraction of numbers in scientific notation. These are the steps to follow. Then what about in multiplication and division? Okay, so let's look at multiplication and division. Multiplication and division. Okay, what if we are multiplying or we are dividing? So the first one, let's say we have 2.1 times 10 to the power 4 multiplied by 3.0 times 10 to the power 2. Okay, so when we are dividing, when we are multiplying, you do the same, you multiply these. So you say 2.1 multiplied by what? 3.0. Then times. We have 10 to the power 4, 10 to the power 2. These are multiplying. Same, let's say we have a to the power 2 multiplied by what? A to the power 3. We apply laws of exponents. Same bases, what do you do to the powers? You add them. So it will be a to the power 2 plus 3. It's the same thing we are doing here. 10 to the power 4, 10 to the power 2. These are same bases. So you simply say 10, then you add the powers 4 plus 2. So let's multiply. What is 2.1 times 3? So 2.1 multiplied by 3, we are getting 6.3. Okay, so 6.3 times 10 to the power 4 plus 2, that's 6. That's it. Okay, we move on to B. For B, we have 4.0 times 10 to the power negative 5 multiplied by, let's say, 6.0 times 10 to the power 3. Okay, let's try this one. So what you do, you multiply these again, so it will be 4 times 6, right? Yes, 4 times 6. Then you multiply by 10 to add to the powers, -5 plus what? 3. Okay, so 4 times 6, it will give us what? That's 24, right? Yes, so 24 times 10 to the power, we have -5 plus 3, that's -2. Then you check if your answer is in standard form. So this is 24, it should be 2.4, the decimal point is there, so it should have 2.4 times 10, what will be the power? Okay, so we have moved this decimal point to the left, meaning we say +1, so it will be to the power -1. That's it. Then for C, let's say we have 9.6. Okay, let's try the one for division now. To the power -3 divided by 3.2 times 10 to the power -4. This is for dividing. So we are applying laws of exponents here. So when we are dividing, let's say a to the power n over a to the power m. What do you do to the powers when you have same bases? It's a to the power n minus what? M, right? You subtract the powers for same bases. Same applies here. You simply divide these. So you get your 9.6, you say over 3.2. Over 3.2, like that. Then multiply by 10 to the power, that's -3 minus, so it should be -3 minus, this minus is in the formula, minus what? -4. Okay, so 9.6, we have 9.6 divided by what? 3.2. 9.6 divided by 3.2, that's simply 3. So we have 3 multiplied by 10. Then here we have -3 plus what? Plus 4, right? Then it will be 3 times 10. What is -3 plus 4, which is simply 1? Eh? Yeah, so that is just 3 times 10 to the power 1. So that's how you go about division of numbers. Okay, let's look at the last one for division. So for division, let's say we have 8.5 times 10 to the power 4 divided by 5.0 times 10 to the power 9. Okay, so here we are dividing, meaning you get your 8.5 there over it's 5 multiplied by 10 to the power 4 minus, so you subtract the powers, that's 9. So what's 8.5? 8.5 divided by 5, I'm getting 1.7. So we have 1.7 multiplied by 10 to the power 4 minus 9, which is actually -5. So that's it. This is how you deal with numbers in scientific notation: addition, subtraction, multiplication, and division. Hope you have gotten the concept. Let's look at significant figures. Significant figures. Okay, so for significant figures, let's just go through the rules. And the first one, which we'll talk about, we're saying all non-zeros are significant. All non-zeros are significant. If you have numbers like 2, 3, 1, 7, 2, 8, all these are non-zero numbers, meaning they are significant. So in this one, for to count the significant figures, it's 1, 2, 3, 4, 5, 6. 6 significant figures. Okay, so that's the first row we have just talked about. And the second one, we are saying all zeros occurring between two non-zero digits are significant. All zeros occurring between two non-zero digits are significant. For example, 20, 501, 201. So these zeros are occurring between non-zero digits. 2 and 1, non-zero digits. 5 and 1, non-zero digits. So even these zeros will be significant. Otherwise, if we have zeros at the end there, they won't be significant. Okay. So in here, if we want to count significant figures, it's 1, 2, 3, 4, 5, 6, 7, 8 just. So it's 8 significant figures. Okay. Then we move on. So the other one, we are saying that if a number starts with a decimal, all the zeros on the left side of the first non-zero digit are not significant, but all zeros on the right are significant. So for example, let's say we have numbers like 0.000124 and another number like 0.003010. Okay, let's say we have these numbers. So we are saying that these zeros for a decimal number, these zeros before a non-zero digit number, they are not significant, but then the zeros that come after a non-zero digit number are significant. So in this case, we have how many significant figures? The first one, it's just 1, 2, 3, 4 significant figures. Then for the second one, we have these zeros which are coming before a first non-digit number. 3 is a non-zero digit number. So these first zeros are not significant, but any other zeros that will come this side will be significant as long as it is a decimal number. So here 1, 2, 3, these zeros are significant. So 1, 2, 3, including 1, 0 and these 3. So we have 1, 2, 3, 4, 5, 6 significant figures. Hope you get the concept there. Okay. Then moving on, we are saying that if a number has an integral part and a decimal part, all zeros in the number are significant. So if you have a number with an integral part and a decimal part, all zeros are significant. So that integral part is simply the whole number part. For example, numbers like 20.10. So this one number part, we are calling it an integral part, and this side, this is a decimal part. So such numbers, even zeros, are significant. So in this one, we have 1, 2, 3, 4 significant figures. Okay. Then let's say we have maybe 50.000. So we have a whole number part this side in decimal point, meaning even all zeros will be significant. So it's 1, 2, 3, 4, 5 significant figures. Okay. Hope you get the concept there. Then the other thing, numbers in scientific notation. So for numbers in scientific notation, all digits in the coefficient are significant. So if we write number in scientific notation like 6.0200 times 10 to the power 4. Another one, let's say 3.050 times 10 to the power 4. So what coefficient are we talking about? This one, before the times 10 to the power something, this one. So all numbers here are significant. All the numbers are significant. Before times 10 to the power anything, all numbers are significant. So in this one we have 1, 2, 3, 4, 5 significant figures. Then for this one we have 1, 2, 3, 4 significant figures. Okay, so that's it. Then we can have numbers like, let me just talk about the last thing under significant figures. We can have numbers like, let's say 5 with 1, 2, 3, 4 zeros. Okay, so for that one, how many significant figures does it have? Of course, when you apply these rules, you find that only 5 is significant. At the same time, we can have a lot of possibilities. So such cases are usually ambiguous. We can have a lot of possibilities for such numbers, whereby we just have a number without a decimal point and all zeros. Yes. So for such numbers, you can have a lot of cases when you're writing what? In scientific notation. So this same number writing in scientific notation, we can say what? 5.0000 times 10 to the power what? The decimal point has moved 1, 2, 3, 4. So for this one, it's how many significant figures? So count 1, 2, 3, 4, 5. We have 5 significant figures. The same number written in standard form, 5 significant figures. What if we have 5 point, let's drop 1 0 there. 1, 2, 3 times 10 to the power 4. So for this one, it will be how many? So for this one, it's 5 significant figures. For this one, it will be 1, 2, 3, 4. 4 significant figures. Then, if we drop another 0, let's say 5.00 times 10 to the power 4, it's the same number. So for this one, it will be 1, 2, 3, 3 significant figures. The same number, we can say 5.0 times 10 to the power 4. For this one, it is 2 significant figures. But if we write it as what? 5 times 10 to the power 4, it will be just 1 significant figure. So as you can see, all these possibilities just for one number like that. So such cases, when you have a number like this, it can be an ambiguous case. No wonder it's important that a number is written in standard form so that you can easily tell the number of significant figures. Okay, so I hope you get the concept there. Okay, so that is it for significant figures. Then what about the rules for addition and what? The rules for handling significant figures. Addition, multiplication, division, and subtraction. So, what are the rules for addition and subtraction when dealing with significant figures? So in dealing with scientific notation, we have talked about addition, subtraction, multiplication, and division. Then what about for significant figures? How do we deal with addition and subtraction? Okay, so let's say we are adding 2.01 grams plus 4.000213 grams. Okay, so for addition and subtraction, you should consider the decimal places. So let's check these numbers we are adding. So this number has been written to how many decimal places? Of course, it's 1, 2. So the numbers after decimal places, 1 after decimal point, 1, 2. So say 2 decimal places. Then this one has been written to how many decimal places? So we count 1, 2, 3, 4, 5. 5 decimal places. After that, we are interested in the result that we obtain after adding these. So after adding these, the final answer should contain the number having the least decimal places. So the least decimal places between 2 and 5, of course, is 2. So meaning the answer should be written correct to 2 decimal places. That's the rule to follow. Okay, so here, let's continue. Let's add. Let me just punch that in the calculator. So we have 2.01 plus 4.000213. So I'm getting 6.010213 grams. This is what I'm getting. The final answer should be written correct to what? 2 decimal places, according to what we started with. So we just count 1, 2 decimal places. 6.01 grams. That is the answer. Okay. Let's do another one. Let's say we have 42.776 meters, then minus 21.12 meters. So if you check, let's check the number of decimal places. So for this one, decimal places 1, 2, 3. 3 decimal places. Then for this one, it's 2 decimal places, meaning the answer should be reported correct to what? 2 decimal places. So this will be equal to 42.776 minus 21.12. So I'm getting 21.656 meters. Now we should consider the decimal places. So this will be equal to what? 2 decimal places. So 1, 2. That will be, we round off correct to 2 decimal places to be 21.66, right? Meters. Okay. So that's it. For addition and subtraction, consider the least decimal places from what you started with. Only least decimal places. Then what about for multiplication and division? Let's also talk about multiplication and division. Multiplication and division. Okay, so for multiplication and division, you consider the least significant figures, different from addition and subtraction. So for this one, consider the least significant figures. Let's say, for example, we have 2.21 multiplied by 5.4. Okay, so for this one, how many significant figures are in this number? It is 3 significant figures, right? Then in this number, how many significant figures in 5.4? It's 2 significant figures. So when you multiply them, the answer should be reported to the least significant figures, which is 2 significant figures. So consider the significant figures. Let's multiply 2.21 multiplied by 5.4. We're getting 11. So we're getting 11.934. Okay, 11.934. So let's round off this one. Okay, so in rounding off this one, we should do counting 2 significant figures to be 1, 2. Then this is 9, which is greater than or equal to 5. So we should add a 1 to this 1 so that we can have what? 12. So we have rounded off correct to 2 significant figures. Then let's say we have 62.45 divided by 31.2. So let's check the significant figures. So in here we have 1, 2, 3, 4. It's 4 significant figures. Then in 31.2, it's how many significant figures? It's 3 significant figures. So the answer should be reported to least significant figures, 3. So here we have 62.45 divided by 31.2. So we're getting 2.0016025664. Then let's count 3 significant figures. It will be 1, 2, 3. So meaning the answer is simply what? 2.00. That's 3 significant figures. So this is how you deal with multiplication and division. Consider the significant figures. Okay. Then let's talk about the last part, which is measurement error or simply uncertainty. Let's talk about measurement error or uncertainty. So we know that errors are simply uncertainties in measurements. When carrying out measurements or experiments, there are errors that occur. Okay, so the first thing we should know is the difference between accuracy and precision. Accuracy and precision. Okay, we start with accuracy. So accuracy refers to how close a measured value is to the true value or standard value of a quantity. Let's say the standard value of the quantity is what? 2.45 grams. Let's say that's the standard value of the quantity. Then you start carrying out experiments. You find 2.40, you find 2.42, you find 2.46. Yeah. So how close these measured values are to the true value, that is what we are calling accuracy. How close a measured value of the quantity is to the true value, that is accuracy. Then what about precision? Let's say the true value is 2.45. Then you measure other values, let's say 2.12, 2.13, 2.14 grams, like that. Yes. So precision simply refers to how close the measured values of the same quantities are with each other. So for precision, we talk about how close those values you are measuring are to each other without even considering the true value. So just consider how close the measured values of the same quantity are to each other. Then accuracy, it's about how close a measured value is to the true value. So it's possible to have values which are precise but they are not accurate. Like for these values here, these values, they are closer to each other. The measured values of the same quantity, which is mass, they are closer to each other. We can say they are precise. But if you compare them to the what? To the true value 2.45, they are not that accurate, but they are precise. Hope you get the difference between accuracy and precision. So I'm repeating again, accuracy is simply how close a measured value is to the true value. Then precision is how close two or more measured values of the same quantity are with each other. Okay, so that's the difference. Then let's also talk about some common types of errors. So for types of errors, there are two which we should keep in mind. We have random error and systematic error. Random error and systematic error. So random error, also called indeterminate error. So this one is also called indeterminate. If you don't find indeterminate, you can find random. If you don't find random, you can also find reproducibility. It's also called reproducibility. Okay, so the same random error is also called what? Indeterminate error or reproducibility error. Then for systematic error, it's what? Determinate error. Determinate error. Okay, then let's differentiate these two. So for random errors, you find that a measurement always has an equal chance of being high or low. So a measurement has an equal chance of being high or low for random errors. Then for systematic errors, a measurement occurs only in what? One direction, in the same direction only. Let's say we have to differentiate them. They are random, systematic. So for a random error, we are saying that a measurement has an equal chance of being high or low. So for this one, a measurement has what? An equal chance of being high or low. Equal chance of being high or low. Then for this one occurs only in what? One direction. This one occurs only in one direction. So occurs in the same direction. So what do we mean when we say for a random error, a measurement has equal chances of being high or low? For example, let's say we are measuring something and it has a true value of 2.0 grams. That's the true value. Then we take the first measurement to be 2.01 grams. Second measurement we find 1.99 grams. Another measurement we find, let's say, 2.011 grams. Another measurement, let's say we find 1.98 grams. So as you can see, we are finding both values which are greater than the actual value and less than the actual value. 1.99 less than the actual value, 2.01 and 2.11 greater than the actual value. So this is what we mean by saying equal chances of being high or low. So meaning the error can be positive or negative. There are equal chances that an error will be positive or negative. We don't know the outcome if the error will be positive or negative. The chances are equal. That is for random errors. Yes. Then for systematic errors occurs in the same direction. If the true value is, let's say, 2.0 grams, then we'll only be getting values which are greater than 2.0. If an error occurs, we can be getting 2.1 grams, maybe 2.11, 2.12, and so on. All values greater than the actual value, which is 2.0. So it's occurring in one direction only. In this case, we can say it's always positive like this, occurring in one direction only. Then in some cases, we can only be getting values which are less than the actual value, meaning occurring in the negative or below, always below, or always low, or always high. Hope you get the difference there. Okay, so for random errors, actually the causes can be due to lack of measurement skill. The experimenter has no measurement skill, can lead to random errors. Then this one usually it's due to faulty equipment. Equipment having faulty, find that systematic errors can occur. So I hope you get the differences between these random and systematic errors, accuracy and precision. Okay, so that's it for this video. Hope you have understood. Thank you for watching.